And now in this lecture we'll answer two questions. In the first question, we'll find out the area of this main triangle ABC. And in the second question, we'll find out the length of this line segment AP that is equals to x. We have to find out the value of x. So we start with the first question. In the drawing, we have quadrangle AQPCB. We know that PC equals to 4 units in its length. This is side AB, that equals to 5 units in its length. This is angle ABC. The size of angle ABC is 60 degrees. This is angle QPC. The size of angle QPC. The size of angle QPC is also 60 degrees. This is angle PQC. Angle PQC equals to 90 degrees in its side. Again, our task is to find out the area of this green triangle, triangle ABC. Okay, so first of all, we will do a construction. That is to say, from this point A, we draw perpendicular on QC. Again, from point A, we will draw perpendicular on QC. So actually, this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees in its size according to our construction. We define the touching point of the perpendicular from point A in QC, this point, as point M. We have actually, this is triangle AQC. Triangle AQC is an associated triangle because side AQ equals to side AC. QC is the base of the associated triangle, triangle AQC. And we have the rule that says that the perpendicular to the base of an associated triangle bisect the base. Again, the perpendicular to the base of an associated triangle bisect the base. So according to the rule that I mentioned, the perpendicular AM to the base QC bisects base QC. That is to say, it divides the base QC into two halves. Each half equals to QC over 2. So QM equals to QC over 2, and MC also equals to QC over 2. That is to say, QM equals to MC, according to the rule that I mentioned. So if we define the length of QM as A, then the length of MC must be also equal to A because they are equal to each other in their lengths, according to the rule that I mentioned. In the next step, we will extend the perpendicular AM by straight line until it touches side PC. And we define the touching point of the extended perpendicular AM with side PC. This point is point N. The perpendicular AM is absolutely a straight line. When we extend the straight line AM by straight line, the result is AN. So when you extend a straight line by straight line, the result must be a straight line. Therefore, AN must be a straight line. So if we focus on the right side of the straight line AN at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the right side of the straight line AN at point M? We have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we focus on the right triangle PQC. In the right triangle PQC, 90 degrees plus 60 degrees is 150 degrees. Therefore, this missing angle, this first missing angle must be equal to 30 degrees in its size, according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the small right triangle NMC, 90 degrees plus 30 degrees is 120 degrees, and therefore this first missing angle must be equal to 60 degrees in its size, according to the sum rule that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to say that the big right triangle PQC is similar to the small right triangle NMC. I will explain anyway why those two right triangles are similar to each other. First of all, this is angle C, that is equal to 30 degrees in its size. Angle C is a common angle that belongs to both triangles. Angle C belongs to the big right triangle PQC, and angle C also belongs to the small right triangle NMC. So angle C is a common angle that belongs to both triangles, so we can write down that angle C equals to itself as a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 60 degrees and therefore they are equal to each other. So if we found out that all the three angles of the big right triangle PQC are corresponding equal to all the three angles of this small right triangle NMC. And therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. We actually found out that the big right triangle PQC is similar, this is the sign of similar, to the small right triangle NMC. According to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side NC of the small right triangle NMC over side PC of the big right triangle PQC is equal to side MC of the small right triangle NMC over side QC of the big right triangle PQC. Okay, again, from the fact that the big right triangle PQC is similar to the small right triangle NMC, we will derive that the following relationship exists between their sides. We will derive that side NC of the small right triangle NMC over side PC of the big right triangle PQC is equal to side MC of the small right triangle NMC over side QC of the big right triangle PQC. NC is the missing side, so we leave it as it is. Over PC. PC equals to 4 units in its length, according to what is given as the question. And it is equal to MC. MC equals to a unit in its length, according to our definition. over side QC. QC equals to A plus A, that is 2A, also according to our definition. So in total we actually found out that NC over 4 equals to A over 2A. So here we have A in the numerator and A in the denominator, so A will get cancelled. After cancelled A, in this side of the equation we left only with 1/2. So 1/2 equals to NC over 4. Or NC over 4 equals to 1/2. Here we will multiply this equation by 4. And finally we get that the missing side NC is equal to 4 over 2, that is 2. So if we found out that the missing side NC is equal to 2 units in its length. So I write it down. NC equals to 2 units in its length. In the next step, I'll copy the big triangle tile NAB in a new page, and we will analyze this big triangle tile NAB. Side AB of triangle A and B equals to 5 units in its length according to what is given as the question. Angle ABC equals to 60 degrees in size, also according to what is given as the question. And we have already found out that angle ANB also equals to 60 degrees in its size. So actually, this is the big triangle A and B that are coming from the original drawing. This big triangle A and B (60 plus 60 degrees is 120 degrees, and therefore this third missing angle must be equal to 60 degrees in its size, according to the rule that states that the sum of the angles in any triangle is equal to 180 degrees. So if you found out that the big triangle NAB is an equilateral triangle. So I write it down. The big triangle NAB is an equilateral triangle. And we know that in any equilateral triangle, all of its sides are equal to each other. So if side AB equals to 5 units in its length, then side NB must be also equal to 5 units, and side AN must be also equal to 5 units in its length. So we actually found out that this is side NB. This is side NB of the equilateral triangle NAB. NB equals to 5 units in its length. So what is the length of the missing side CB? From the drawing it is very easy to see that CB in total equals to NB minus NC. Again, NB minus NC equals to CB. So I write it down. We actually found out that CB equals to NB minus NC. So CB in total equals to NB, that is 5, minus NC, that is 2. So in total, CB equals to 5 minus 2, that is 3. CB equals to 3 units in its length. This is side CB, that equals to 3 units in its length. In the next step, we will do another construction, that is to say from point A, we will do perpendicular on CB. Again, from point A, we will do perpendicular on CB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point A and CB. This point is point O. In the next step, we define the length of line segment AO of side AO as H. It's actually AO is the height to the base CB. So in the next step, I'll copy the right angle triangle AOB in a new page, and we'll find out the length of the missing side AO that equals to H. AO equals to H, according to our definition. The hypotenuse AB equals to 5, according to what is given as the question. Actually, this is the right angle AOB that are coming from the original domain. According to what is given as the question, again, ABC equals to 60 degrees in its size. So in this triangle, the right angle AOB, the sine of 60 degrees is equal to AO over AB. So sine of 60 degrees equals to AO equals to H according to our definition, over AB equals to 5. So in total we actually found out that sine of 60 degrees equals to H over 5. Sine of 60 degrees equals to H over 5. Sine of 60 degrees equals to the square root of 3 over 2. So the square root of 3 over 2 is equal to H over 5. Here we will multiply this equation by 5. And we get that H equals to 5 times square root of 3 over 2 units in its length. H equals to 5 times square root of 3 units in its length. Our task is to find out the area of this great triangle ABC. We will choose the base of this triangle ABC as CB, and therefore the area of this triangle ABC must be equal to the base CB times the height to the base, that is h, over 2. Again, the area of this green triangle ABC, is equal to the base CB times the height to the base, that is h, over 2. We have already found out that CB equals to 3 units in its length times h. We have already found out that h equals to 5 times root of 3 over 2, and we have to divide it by 2. Divided by 2. So in total, we have found out that the area of this green triangle ABC is equal to either, here we have 3 times 5 is 15, so in total in the numerator of this expression we have 15 times root of 3 over 2 times 2, that is 4. So if you found out that the area of this triangle ABC is equal to either 15 times root of 3 over 4 square units in its size, or in terms of numbers, is equal to 6.5 square units in its size. So repeat again, if you found out that the area of this green triangle ABC is equal to either 15 times root of 3 over 4 square units in its size, or in terms of numbers, the area of this green triangle ABC is equal to 6.5 square units in its size. So we finish with the first question. In the next step, I will present to you the second question, and we will solve the second question of this lecture. In the second question, our task is to find out the length of this line segment AEP that is equals to x. We have to find out the value of x. So in the drawing we have a semicircle. Point O is the center of this semicircle. This is line segment PO that is equals to 10 units in its length. This is line segment QP that is equals to 21 units in its length. This is chord QS that is equals to 6 units in its length. This is angle PQS that is a right angle. Again, our task is to find out the length of this line segment AEP that is equal to x. So first of all, we will complete this semicircle to a circle. So we completed the semicircle to a circle. In the next step, we will extend line segment QP by a straight line until it touches the circle. And we will define the touching point of the extended line segment QP with this circle. This point is point M. In the next step, we will join points S and M together by a straight line. So by doing all those constructions, we can do triangle SQM. This is triangle SQM. peripheral angle SQM equals to 90 degrees in its size, and peripheral angle SQM subtend on chord SM. Again, peripheral angle SQM subtend on chord SM. Here we can implement rule 5 in our drawing. I'll repeat quickly on rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees must subtend on the diameter of the circle. In the drawing, you have a circle. This is peripheral angle MAN that is equal to 90 degrees in its size, and therefore peripheral angle MAN must subtend on the diameter of this circle, and indeed peripheral angle MAN subtend on MN, that is the diameter of this circle. So according to rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. So we can implement rule 5 in our drawing. In our drawing, this is peripheral angle MQS that is equal to 90 degrees in its size, and therefore peripheral angle MQS must subtend on the diameter of this circle. Peripheral angle MQS subtend on MS, and therefore according to rule 5, MS must be the diameter of this circle. So we found out that chord MS is the diameter of this circle according to rule 5. Chord MS is the diameter of this circle according to rule 5. So we know that point O is the center of this circle, point S is the point of this on this circle itself. Therefore, OS is the radius of this circle. We define the radius of this circle as R, so OS equals to R. Likewise, OM is also the radius of this circle, and therefore it is equal to R. In the next step, we will do another construction. That is to say, from point O, that is the center of this circle, we will draw perpendicular on QP. Again, from point O, we will draw perpendicular on QP. So actually, this angle equals to 90 degrees in its size, and this angle must be also equal to 90 degrees in its size according to our construction. We will define the touching point of the perpendicular from point O and QP. This point is point N. We have here this angle M. We will define this angle M as alpha. Actually, angle M that is equal to alpha is a common angle that belongs to the big triangle SQM. This is the big right triangle SQM. Angle M also belongs to the small right triangle ONM. So angle M is a common angle that belongs to both triangles. So we'll focus on the big right triangle SQM. On the big right triangle SQM, this is angle alpha. This angle equals to 90 degrees in its side, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the small right triangle ONM, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. So in the next step, we'll prove that the big right triangle SQM is similar to the small right triangle ONM. Actually, it is very easy to see it from the drawing itself, but I will prove it anyway. So why the big triangle SQM is similar to the small right triangle ONM? First of all, this is angle M, that is a common angle that belongs to both triangles. So I can write down that angle M equals to itself as a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if you found out that all the angles of the big right triangle SQM are corresponding equal to all the angles of the small right triangle ONN. And therefore those two right angles are similar to each other according to angle similarity rule. So I write it down. We actually found out that the big right triangle SQM is similar, this is the sign of similar, to the small right triangle NOM according to angle similarity rule. And from the fact that the big right triangle MQS is similar to the small right triangle MNO, we will derive that the following relationship exists between their sides. We will derive that side NO of the small right triangle NOM over side QS of the big right triangle SQM is equal to side OM of the small right triangle NOM over side SM of the big right triangle SQM. So if it begins from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We will derive that side ON of the small right triangle NOM over side QS of the big right triangle SQM is equal to side OM of the small right triangle NOM over side SM of the big right triangle SQM. ON is the missing side, so we leave it as it is, over QS. According to what is given to the question, QS equals to 16 units in its length. QS equals to 16. And it is equal to OM. OM is the radius of this circle that is equal to R, according to our definition, over SM. SM is the diameter of this circle that is equal to 2R. So in total, we found out that ON over 16 equals to R over 2R. So we have R in the numerator and R in the denominator, so R will get cancelled. So in this end of the equation, we left only with 1/2. So 1/2 equals to ON over 16. Or ON over 16 equals to 1/2. Here we will multiply this equation by 16. And finally we get that the missing side ON is equal to 16 over 2, that is 8. So if you found out that the missing side ON is equal to 8 units in its length. So this is the missing side ON, that is equals to 8 units in its length. In the next step, I'll copy this right triangle NPO in a new page, and we'll implement the Pythagoras theorem on this small right triangle NPO. Here by PT is the progression from Pythagoras theorem. The hypotenuse PO equals to 10 units in its length according to what is given as the question. PN is the missing side, and NO equals to 8 units in its length according to what we already found out. So actually, this is the right small triangle NPO that I copied from the original domain. In this small right triangle NPO, according to the Pythagoras theorem, PO squared, that is the square of the hypotenuse, is equal to NP squared plus NO squared. And again, according to the Pythagoras theorem, in this right triangle NPO, PO squared, that is the square of the hypotenuse, equals to NP squared plus NO squared. PO equals to 10, therefore PO squared is 10 squared, that is 100. And it is equal to NP squared. NP is the missing side, so we leave it as it is. So it is NP squared plus NO squared. NO equals to 8, therefore NO squared is equal to 8 squared, that is 64. So in total we should find out that 100 equals to NP squared plus 64. Here we will subtract 64 from this equation, and finally get that NP squared equals to 100 minus 64 is 36. So NP squared equals to 36. Here we take a root out of this equation, and finally get that the missing side NP is equal to the square root of 36, that is 6. So if you found out that the length of the missing side NP, the length of this missing side NP is equal to 6 units. What is the length of the missing 9 segment QN? From the domain it is very easy to see that QN in total equals to QP minus NP. Again, QP minus NP equals to QN. So I write it down. I have found out that QN is equal to QP minus NP. So QN in total equals to QP, according to what is given as the question, QP equals to 21 units in its length. Minus NP. We just right now found out that NP equals to 6 units in its length. So in total we should found out that QN equals to 21 minus 6, that is 15. QN equals to 15 units in its length. this is the missing side QN, that is equal to 15 units in its length. In the next step, I'll join points O and Q together by straight line. Point O is the center of this circle, point Q is the point of the circle itself, therefore OQ is the radius of this circle. We define the radius of this circle as R, so OQ equals to R. In the next step, I'll copy the right triangle Q and O in a new page, and we'll implement the Pythagoras theorem on this right triangle Q and O. So this is the right green triangle Q and O. The hypotenuse QO is the missing side. That is also the radius of this circle is equals to R. And all side and all of the green right triangle Q and O is equals to 8 units in its length. And we just write our formula, the Qn equals to 15 units in its length. Here by PT is the progression for Pythagoras theorem. So actually, this is the right green triangle Q and O that I copied from the original drawing. This right triangle Q and O. QO squared, that is the square of the hypotenuse, equals to QN squared plus NO squared. So I write it down. QO squared, that is the square of the hypotenuse, is equal to Qn squared plus NO squared. QO is also the radius of the circle that is equals to R, therefore QO squared is R squared, and it is equals to Qn squared. Qn is 15, therefore Qn squared is 15 squared, that is 225, plus NO squared. NO is 8, therefore NO squared is 8 squared, that is 64. So in total we should find out that R squared equals to 225 plus 64. 225 plus 64 is 289. So I should find out that R squared equals to 289. Here we will take a root out of this equation and finding out that the radius R of the circle equals to the square root of 289, that is 17. So if you found out that the radius R of this circle is equal to 17 units in its length. OA is also the radius of this circle, that is equal to R. So the radius of this circle R is equal to 17. OA is also the radius of the circle that is equals to R, and R equals to 17. But OA is also equal to OA equals to AP plus PO. Again, OA in total equals to AP plus PO. So I write it down. OA equals to AP plus PO. Again, OA equals to AP plus PO. AP is the line segment that we are looking for in this question, and it is equals to X plus PO. PO equals to 10 units in itself, according to what is given us the question. From this long equation, we will derive that 17 equals to X plus 10. Again, 17 equals to X plus 10. 17 equals to X plus 10. Here we will subtract 10 from this equation, and finally we get that X, that is the line segment that we are looking for, X is actually equals to AP is equal to 17 minus 10 is 7 units. So the answer to the question is that the length of this line segment AP that is equals to X is 7 units. And that is the answer to the second question. So in the next step, I will summarize the lecture. We'll start with the first question, of course. In the first question, our task was to find out the area of this green triangle, triangle ABC. So in the domain, we have quadrilateral QABCP. It is given us the question that AQ equals to AC. We also know that this is angle QPC, that is equals to 60 degrees inside. This is angle ABC, that is also equals to 60 degrees inside. And this is angle PQC, that is a right angle. In addition, we know that this is line segment PC, that is equals to 4 units in itself. This is a side AB or line segment AB, that is equals to 5 units in itself. Again, our task is to find out the area of this green triangle, triangle ABC. In the first step, we did the construction. That is to say, from point A, we go perpendicular on QC. Again, from point A, we go perpendicular on QC. So here this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to our construction. We define the touching point of the perpendicular from point A and QC. This point is point M. Actually, triangle QAC is an associated triangle because side AQ equals to side AC. And QC is, of course, the base of this associated triangle, triangle QAC. And we have the rule that says that the perpendicular to the base of an associated triangle bisect the base. Again, the perpendicular to the base of an associated triangle bisect the base. So according to the rule that I mentioned, the perpendicular AM to the base QC of the associated triangle, triangle QAC bisect the base QC. That is to say, the perpendicular AM divides the base QC into 2 halves. Each half equals to QC over 2. So the first half QM is equals to QC over 2, and the second half MC also equals to QC over 2. So if we define the length of QM, say, then the length of the second half MC must be also equal to A. So in the next step, we extended the perpendicular AM by side line until it touches side PC. At this point, we define the touching point of the extended perpendicular AM with side PC. This point is point N. So here, AM is a perpendicular, it is absolutely a straight line. So when we extended the straight line AM by straight line, the result is AN. When you extend the straight line by straight line, the result must be a straight line. Therefore, the result AN is a straight line. So if you focus on the right side of the straight line AN at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the right side of the straight line AN at point M? We have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. If we focus on the right triangle PQC, 90 degrees plus 60 degrees is 150 degrees, and therefore this third missing angle must be equal to 30 degrees in its size according to the rule that states that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the right small triangle NMC, 90 degrees plus 30 degrees is 120 degrees, and therefore this third missing angle must be equal to 60 degrees according to the sum rule. So it is very easy to see that the big right triangle PQC is similar to the small right triangle NMC. I will prove it anyway. So why the big right triangle PQC is similar to the small right triangle NMC? First of all, this is angle C that is equals to 30 degrees in its size. Angle C is a common angle that belongs to both triangles. So we can write down that angle C that is equals to 30 degrees in its size is a common angle that belongs to both triangles. It is equals to itself as a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 60 degrees and therefore they are equal to each other. So if you found out that all the three angles of the big right triangle PQC are corresponding equal to all the three angles of the small right triangle NMC. And therefore those two right angles are similar to each other according to angle similarity rule. So if it again, we can find out that the big right triangle PQC is similar, this is the sign of similar, to the small right triangle NMC according to angle similarity rule. And from the fact that those two right triangles are similar to each other, that is to say that the right big triangle PQC is similar to the right small triangle NMC, we derive that the following relationship exists between their sides. We will derive that side NC of the small right triangle NMC over side PC of the big right triangle PQC is equal to side MC of the small right triangle NMC over side QC of the big right triangle PQC. So if again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side NC of the small right triangle NMC over side PC of the big right triangle PQC is equal to side MC of the small right triangle NMC over side QC of the big right triangle PQC. NC is the missing side, so we leave it as it is. PC equals to 4 units in its length according to what is given as the question. And it is equal to MC. MC equals to A units in its length according to our definition over QC. QC equals to A plus A, that is 2A. So in total, we found out that NC over 4 equals to A over 2A. We have A in the numerator and A in the denominator, so A will get cancelled. So in this side of the equation, we left only with 1 half. So 1 half equals to NC over 4. If we multiply this equation by 4, and finally found out that NC, the missing side NC equals to 4 over 2, that is 2. So this is the missing side NC, that is equals to 2 units in its length. In the next step, I copied the big triangle NAB in a new page, and we analyze this big triangle NAB. So actually, this is the big triangle NAB that I copied from the original domain. Side AB equals to 5 units in its length according to what is given as a question. It is given as the question that angle AB is, this is angle ABN, that is equals to 60 degrees in size. This is angle ANB, that is also equals to 60 degrees in size according to what we have already found out. So 60 degrees plus 60 degrees is 120 degrees. Therefore, this third recent angle must be equal to 60 degrees in size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Therefore, this third recent angle must be equal to 60 degrees in its size. So actually found out that the big triangle A and B is an equilateral triangle because of the fact that all of its angles are equal to each other. And we know that in any equilateral triangle, all the sides are equal to each other. Side AB equals to 5, and therefore side AN must be also equal to 5, and side NB must be also equal to 5 units in its length. In the next step, we did another construction, that is to say from this point A, we do perpendicular on CB. Again, from point A, we do perpendicular on CB. But what is the length of CB? CB in total equals to NB minus NC. Again, CB equals to NB minus NC. So CB equals to NB, that is 5. It is one side of the equilateral triangle A and B. Minus NC, that is 2. So in total, CB equals to 5 minus 2, that is 3. Again, CB equals to 3 units in its length. So in the next step, we did a construction, that is to say from point A, we do perpendicular on CB. Again, from point A, we do perpendicular on CB. So by doing this construction, we're going to do the right triangle AOB. We define the length of side AO as H. So in the next step, I copied the right triangle AOB in a new page, and we found out the length of side AO of this right triangle AOB. So okay, this is the right triangle AOB that I copied from the original drawing. In this triangle AOB, sine of 60 degrees equals to AO over AB. Again, sine of 60 degrees equals to AO over AB. AO equals to H according to our definition. AB, the opposite AB equals to 5 units in its length according to what is given as the question. So in total, we found out that sine of 60 degrees equals to H over 5. Sine of 60 degrees is square root of 3 over 2. So square root of 3 over 2 equals to H over 5. Here we multiply this equation by 5 and found out that H, the missing side H, is equal to 5 times square root of 3 over 2 units in its length. AO is equal to H is equal to 5 times square root of 2. H equals AO is equal to H is equal to 5 times square root of 3 over 2 units in its length. Our task is to find out the area of this green triangle ABC. The area of this green triangle ABC must be equal to the base CB times the height H over 2. Then again, the area of this green triangle ABC must be equal to the base CB times the height H over 2. CB equals to 3, H equals to 5 times square root of 3 over 2 divided by 2. So in total, if you found out the area of this green triangle ABC, it is equal to, we have 3 times 5 is 15. So in the amount of this expression, we have in total 15 times square root of 3 over 2 times 2, that is 4. So in total, we actually found out that the area of this triangle ABC, it is equal to either 15 times square root of 3 over 4 square units in its size. On terms of numbers, the area of this triangle ABC is equal to 6.5 square units in its size. So we finished with the first question. In the next step, I presented to the second question, and we solved the second question of this lecture. In the second question, our task is to find out the length of this small line segment AP that is equal to x. We have to find out the value of x. So in the drawing, we have a semicircle. Point O is the center of this semicircle. Line segment PO equals to 10 units in its length. We also know that line segment QP equals to 21 units in its length. This is called QS, that is equals to 16 units in its length. In addition, we know that this is angle this is angle PQB angle PQB equals to 90 degrees in its size. Angle PQB equals to 90 degrees in its size. Again, our task is to find out the length of this small line segment AP that is equals to x. We have to find out the value of x. So in the first step, we completed the semicircle to a circle, and we extended line segment QP by a straight line until it touches the circle. We define the touching point of the extended line segment QP with this circle. This point is point M. In the next step, we join points S and M together by a straight line. So here we can implement rule 5. According to rule 5, actually by doing all those constructions, you can deduce peripheral angle SQM. This is peripheral angle SQM that is equal to 90 degrees in its size. So here you can implement rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. Again, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. So actually we have here peripheral angle SQM that is equal to 90 degrees in size, and therefore it must subtend on the diameter of this circle. Peripheral angle SQM subtend on SM, and therefore according to rule 5, SM must be the diameter of this circle. Okay? SM is the diameter. Point O is the center of the circle. Point S is the point of the circle itself. Therefore, OS is the radius of this circle. We define the radius of this circle as R. So OS equals to R. Likewise, OM is also the radius of this circle, and therefore it is equals to R units in its length. In the next step, we did the construction. That is to say, from point O, that is the center of this circle, we do perpendicular on QP. Again, from point O, we do perpendicular on QP. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. When you find the touching point of the perpendicular from point O and QP, this point is point N. So here we have, this is angle N, that is a common angle that belongs to both triangles. Angle M belongs to the small right triangle O and M. Angle M also belongs to the big right triangle SQM. So angle M is the common angle that belongs to both triangles. We define the common angle M as alpha, and focus on the big right triangle SQM. In the big right triangle SQM, this angle equals to alpha, this angle equals to 90 degrees, and therefore this vertex angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the small right triangle O and M, this angle equals to alpha, this angle equals to 90 degrees, and therefore this vertex angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Actually, it is very easy to see that the big right triangle SQM is similar to the small right triangle O and M. I'll prove it anyway. Why the big right triangle SQM is similar to the small right triangle O and M. First of all, this is angle M, that is a common angle that belongs to both triangles. So you can write down that angle M equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if you found out that all the figures of the big right triangle SQM are correspondingly equal to all the figures of the small right triangle O and M. And therefore, those two right triangles are similar to each other according to angle similarity rule. So repeat again, if you found out that the big right triangle SQM is similar, this is the sign of similar, to the small right triangle NOM according to angle similarity rule. And from the fact that the big right triangle SQM is similar to the small right triangle O and M, we will derive that the following relationship exists between their sides. We will derive the side NO of the small right triangle NOM, or side QS of the big right triangle SQM is equal to side OM of the small right triangle NOM, over side SM of the big right triangle, triangle SQM. So again, we learned that side ON of the small right triangle NOM over side QS of the big right triangle SQM is equal to side OM of the small right triangle NOM over side SM of the big right triangle, triangle SQM. ON is the missing side, so we leave it as it is. SM is the diameter of this. We have here ON is the missing side, therefore we leave it as it is. SQ equals to 16 units in its length according to what is given in the question. And it is equal to OM. OM is the radius of this circle, that is equal to R according to our definition, over SM. SM is the diameter of the circle, therefore it is equal to 2R. So in total we should find out that ON over 16 equals to R over 2R. We have R in the numerator and R in the denominator, so R will get cancelled. So in this side of the equation we left only with 1/2. 1/2 equals to ON over 16. Here we multiply this equation by 16 and finally found out that the missing side ON equals to 16 over 2, that is 8. So this is the missing side ON. It equals to 8 units in its length. In the next step, we implemented the Pythagoras theorem on this small right triangle, triangle OPN. So we call it the small right triangle OPN in a new page, and we implemented the Pythagoras theorem on this small right triangle, triangle OPN. This is the small right triangle OPN that I covered from the original drawing. The hypotenuse OP equals to 10 units in its length. We just right now found out that ON equals to 8 units in its length, and PN is the missing side. According to the Pythagoras theorem on this right small triangle OPN, OP squared, that is the square of the hypotenuse, equals to PN squared plus NO squared. OP is 10, therefore OP squared is 10 squared, that is 100, and it is equal to PN squared. PN is the missing side, so we leave it as it is, plus ON squared. ON is 8, therefore ON squared is 8 squared, that is 64. So in total we should find out that 100 equals to PN squared plus 64. Here we subtract 64 from this equation, and finally found out that NP squared equals to 100 minus 64 is 36. So NP squared equals to 36. Here we took out a root out of this equation, and finally found out that the missing side NP equals to the square root of 36, that is 6. So actually, this is the missing side NP, that equals to 6 units in its length. NP equals to 6 units in its length. What is the length of the missing side QN? From the drawing it is very easy to say that QN equals to QP minus NP. Again, QN equals to QP minus NP. Repeat again. QN equals to QP minus NP. So QN equals to QP. QP equals to 21 units in its length. Minus NP. We just right now found out that NP equals to 6 units in its length. So in total QN equals to 21 minus 6, that is 15. QN equals to 15 units in its length. This is the missing side QN, that equals to 15 units in its length. In the next step, we join points Q and O together by straight line. Point O is the center of the circle, point Q is the point of the circle itself, therefore OQ is the radius of this circle, that is equals to R according to our definition. In the next step, I copied the green right triangle QON in a new page, and we implemented the Pythagoras theorem on this green right triangle QON. So actually, this is the green right triangle QON that I copied from the original drawing. This green right triangle QON, QO squared, that is the square of the hypotenuse, equals to QN squared plus NO squared. QO is the radius of the circle, that equals to R, therefore QO squared is R squared, and it is equals to QN squared. QN is 15, therefore QN squared is 15 squared, that is 225, plus ON squared. ON is 8, therefore ON squared is 8 squared, that is 64. So in total, we actually found out that R squared equals to 225 plus 64. 225 plus 64 is 289. So we found out that R squared equals to 289. Here we took out of this equation, and we found out that R, the radius of the circle, is equal to the square root of 289, that is 17. So we found out that the radius of this circle r equals to 17 units in its length. OA is also the radius of this circle that is equal to r. OA is the radius of the circle that is equal to r, and r equals to 17. But OA in total equals to AP plus PO. Again, OA equals to AP plus PO. And again, OA equals to AP plus PO. AP equals to X. That is the line segment that we are looking for in this question. And PO equals to 10. Again, AP equals to X and PO equals to 10. And from this long equation, 17 equals to R equals to OA equals to AP plus PO equals to X plus 10. We will derive that 17 equals to X plus 10. 17 equals to X plus 10. If we subtract 10 from this equation, and finally found out that X, that is the line segment that we are looking for in this question, X is equals to AP is equal to 17 minus 10, that is 7. So if you found out that the length of this line segment AP is equals to X is equal to 7 units. Okay, thank you very much.